Hi, I'm Jim Heffron. These are my lessons in Calculus 2, and we're, very exciting. We're on the last chapter of the course, rounding the last turn, coming down the home stretch. And what's especially exciting is that this chapter is way easier than the last chapter. So today we're going to do an operation on vectors. We're going to basically find the angle between two vectors. All right, let's get started. So let's see here. The angle between two vectors in 2D, we are given two vectors on the left. There's a u and a v, and you can, of course, put them in whatever position you like. So I'm choosing to put them in canonical position. That is, I'm choosing to have them start at the origin. And then there's an angle between them, theta there. So this is a regular plane geometry. I'm in the plane, so I can apply all the laws that a person learns in high school plane geometry, and one of them is the law of cosines. The law of cosines is a generalization of the Pythagorean theorem. It says that even when you have a non-right angle theta, you still have some kind of relationship between the square of the side opposite that angle and the square of the other two sides. And there it is. That's the extra, the extra part of the equation that makes the equation come out right. Theta is the angle between the two vectors. So that's 2 times the length of u, the length of v, and the cosine of theta. Okay, so I want to solve that equation for theta, basically, because I want to find the angle. So to solve it for theta, let's see, I'm going to expand the left-hand side. Here we go. So of course the square of the length is a square root, so the square of the square root gets rid of the square root. So I'm looking at the difference in the first components squared and the difference in the second components squared. There it is, I squared it out. Okay, and I squared out the second components also. All right, so that's the left-hand side expanded. Now we're ready for the right-hand side expanded. Same thing, this would be a square root, and when you square it, you get rid of the radical. This is a square root, and when you square it, you get rid of the radical. There it is, the expressions without the radical. And then the part that, the remainder part, the part that's left. Okay, so I have a left-hand side and a right-hand side, and I'm going to cancel whatever cancels. So I see, for example, that the u1 squared and u1 squared cancel, because one's on the left and one's on the right. There's a u2 squared and a u2 squared, left and right. I can cancel those. There's a v1 squared and a v2 squared, and a v1 squared and a v2 squared, so I can cancel those. And so I'm left with a left-hand side that has two terms, a minus 2 u1 v1 and minus 2 u2 v2, and the right-hand side has a single term, minus 2 length u length v cosine theta. Cancel the minus 2's. I mean, just do sort of the obvious algebra, and then divide by length u length v, and you're looking at here that theta is the arc cosine of, there's the u1 v1, see the u1 v1, there it is. There's the u2 v2, see the u2 v2, there it is. And when I divided, I had a length u length v on the bottom. Okay, so we solved basically for theta, and we solved for cosine theta, and then we expressed it as an arc cosine relationship. But anyway, we solved for theta, and that's what we got. We just simply got what we got. The u1 v1 comes because the algebra just works out that way. That's the middle terms of a square, and the u2 v2 likewise. The algebra just works out that way. Okay, so I'm interested in the numerator of that expression. So I'm going to think about the numerator of that expression first before we go on to the formula. So let's see, the same equation is going to hold in higher dimension because the two vectors determine a plane and the action happens in that plane. This is one of those 3D things, and it has been my experience that sometimes folks have a little trouble with 3D in this course, just making their brain think 3D-ish. So I took the same picture in a context where I can manipulate it. I can manipulate it, but I can't draw on this context, basically. So if I click on that, then you see that the two vectors determine a plane. I put the two vectors at the origin and they determine a plane, and that's a regular plane. I mean, that's a high school geometry plane. I can do all the high school geometry stuff in that plane and ignore the rest of 3-space. So that's what I'm going to do. I'm going to work inside that plane. When I work in that plane, then exact same stuff happened on the previous slide. I'm not going to click back to it. I'm just working in that plane. So in that plane, in R3, I happen to get this. Vectors are 3 tall, so there's a u1 v1 and a u2 v2, but there's also a u3 v3. but everything else is the same. And so I'm interested in the operation that's in the numerator of this expression. Okay, so that operation is called a dot product because you see the dot there? See the dot there? That's called the dot product or scalar product or inner product of a pair of n component vectors. And you just simply take the two first components and multiply them all the way out to the two last components and multiply them and then add them all up. That's it. That's just simply what dropped out of the algebra. It's just what we got. That's all. So I'm not, didn't rely on a brilliant stroke of insight. It's just I did the algebra, and that's just what I was left with. Okay, so let's see. Just to do an example, 1, 2, 3, 4. You multiply the 1 and the 3. You multiply the 2 and the 4, and you add, and it just comes out to 11. 1, 2, 3, 4, 5, 6 comes out to 32 in the same way. 1 times 4, 2 times 5, 3 times 6. Now it says scalar product up here, so I want to refer to the word scalar. Scalar is a member of whatever number system we use to make the vectors. If the vectors have real number entries, like they do in this course, then scalar means a real number. If the vectors have complex number entries, like they might in a linear algebra course, then a scalar will mean complex numbers. And in this class, we stick to reals. Scalar is because those are the things that are used to rescale a vector. But anyway, it's just a word. The term scalar product brings out a point, and the point is right here, is that we're combining two vectors, but we're not getting a vector out the other end. I mean, this is not like, addition of vectors where you add two vectors and you get a vector. This is you combine two vectors and you get a real number. Because the dot product of two vectors does not return a vector, it returns a scalar. And the next class will cover an operation that's called a vector product because it combines two vectors to return a vector, but that's for the next class. So the dot product of a vector with itself is the square of the vector's length. If you take a vector dotted with itself, then you multiply the first terms all the way out to multiply the nth terms, and that's just clearly the square of the vector's length. So right away we see that dot product arises in a number of ways, and the way I had it arise is I just did the algebra. Here's another way, is that dot product is a generalization of the operation of length. Okay, so practice. And I urge you, as always, to pause the video, take out a piece of paper, give them a whack, and you come back and you'll see hopefully correct answers, and you can check your work. And so when you get to the homework, you'll feel like you have a running start on at least the first couple questions. Okay, please, I'll give you a second to pause the video. Okay, great. So first one is 1 times 2, 3 times minus 5 equals minus 13. And you've noticed, right, that this dot here is, I made it distinctly bigger than a multiplication dot. Just trying to help a person figure out what's what. That's not necessarily true if you get on the internet and you look at somebody else's presentation. It can sometimes be a little hard to tell, but I'm trying to make it quite clear. All right, next one, 2, 0, minus 1, 1, 1, 4. So multiply the first components, multiply the second components, multiply the third components, add it up, and I happen to get minus 2. It's just a number. And here, this is the mistake that I'll see here, is that sometimes people will say something like, well, 3, 1, and there's nothing to put by the 5, so I'll just call it a 0. But that's different. 3, 1, 0 is a vector that's is a vector in 3 space. 3, 1 is a vector in 2 space. They're simply different. Okay, so 3, 1 dot product with 2 minus 1, 5 is undefined. That means it's not a sensible operation. And the next one, find the dot product of these 4-dimensional vectors. And again, I'll pause for a second. All right, and it's not surprising. You multiply the first components, multiply the second components, etc., and I got 6. But just to make the point here, what's happening is that we are doing an operation in 4-dimensional space without drawing any pictures. I mean, in 4-dimensional space, we'd be kind of in a clinch there to draw a picture. But anyway, with it, we don't have to. We're doing an algebraic operation, and we're just simply punching numbers. Next one. Okay, so here I have a vector that is I plus j plus 4k, and you can see one of the reasons why calculus books like this notation is that if I wrote it as ijk as a vertical vector, then it would take up much more vertical room, and calculus books don't want to take up much more vertical room because they're already pretty heavy. They're already pretty thick if you use a physical book. But anyway, this is the same as the vector 1, 1, 4. And if you dot product it with 1, 1, 4, You know, 1 times 1, 1 times 1, and 4 times 4, add them up. 18. Okay, last one. Okay, great. So you're taking 1 times 3, 2 times y, 2 times 6, adding them up and equals 20. That's the equation. You solve it, you get y. I got 5/2. Okay, so we've practiced with dot product operation, and it's time to put down, you know, sort of all the obvious algebraic rules. So all of these vectors are going to have the same number of entries, meaning that v times v dot product with u is going to be defined. That's all. So first of all, dot product is commutative. If you take v dot u or you take u dot v, doesn't matter, you'll get the same result. Dot product with the zero vector is equal to the zero vector. Pardon me, I misspoke. Dot product with the zero vector is equal to the zero scalar. Sorry, I misspoke. Apologize about that. That's a zero scalar. The dot product operation allows scalars to factor out. If you take 5 times v and dot it with u, that's 5 times v dotted with u. Likewise, if you took v dotted with 5u, that would be 5 times v dotted with u. Okay, and the dot product operation distributes over addition. So u dot v plus w is u dot v plus u dot w. So it looks like high school distributive law. All of those rules, all of the rules that are here, are easy to check. And just to do an example, I did commutativity, but they're all similar. So v dot u, I'm multiplying the first components all the way out to multiplying the nth components. But in regular real number multiplication, you can turn those around, and instead of v1 u1, you could write it as u1 v1 and all the way down the line. And of course, then what I have on the right-hand side is the formula for u dot v. So all very easy. There is one subtlety, though, and that subtlety occurs right here in this, and in the other one in Rule 4, but right here. And that is that if you look at this right here, maybe a person who programs a lot has got their antenna tuned to this. This is between two vectors. So this is vector addition. But right here, this is between two scalars. Remember that that's a scalar and that's a scalar. So this is between two scalars. So that's real number addition. So there's a little bit tricky there, is that that one formula contains two different meanings for the plus sign. Okay, anyway, worth a mention. It won't ever trouble us. We won't ever get confused, but worth a mention. Okay, so we're ready for the point here, the angle between two non-zero vectors. Both of them have to be n tall vectors, the same n. So you can't have a 3 tall vector and a 5 tall vector. They have to both be the same tall. But once you have that, it's u dot v in the numerator and length u, length v in the denominator. And of course, we did the development of why the formula holds a couple minutes ago, so I'm not going to do it again. Because the angle theta is gotten as an arc cosine, I know that arc cosine returns outputs between 0 and pi inclusive. If one or both of u and v is the zero vector, it does say two non-zero vectors. If one or both of the two is the zero vector, then the angle just isn't defined, but we're going to have a little bit to say below. Okay, just simply suppose that I drew the zero vector here. That zero vector is just a single point, and then I also drew some other vector, say that the 2 over and 1 up vector, and I asked you what's the angle between them. You'd say it doesn't make sense because I can't put a protractor on the zero vector. It just doesn't make sense. Nonetheless, we'll have a little bit more to say about this down below. So we'll find an angle between the two vectors, and the only real question is how tall are these vectors? 3i plus 2j is a minus 2j is a 3 minus 2 vector, and 5i minus 1/2 j is a 5 minus 1/2 vector. Now, that you can tell, I mean, strictly speaking, I suppose it could be 3i minus 2j plus 0k, but you're just supposed to take me for, you know, for I would have warned you if that was true. So we're taking those to be too tall vectors. And when you do take them to be too tall vectors, the computation is just following the formula on the top of the page here, and I happen to get 0.488 radians. Anybody can make a mistake, but I happen to get 0.488 radians. Okay? So, so corollary of the formula here is that orthogonal means right angles, and so right angles, it means that the dot product, right angles here, means that the cosine for right angles, the cosine is going to be 0. Remember what cosine looks like? The graph of cosine looks like so in the region of interest. And so this is pi over 2, right angle. So right angle means the cosine is 0, and the way this fraction gets to be 0 is to have a 0 numerator. So two vectors are orthogonal if and only if their dot product is 0. Two vectors are parallel if and only if their dot product equals the dot product of their length. So the way you get to be parallel is to be an angle of 0 or else an angle of pi. Angle of 0 or else an angle of pi. Sorry, I had a little trouble with the pen. Angle of pi. And so two vectors are parallel if and only if their dot product equals the product of their lengths. So you got a cosine of 1. If the fraction comes out to be 1, then you got to have that the numerator and denominator equal. So because of that corollary, it's convenient to take the 0 vector to be orthogonal to all vectors, because if you had, say, u was the 0 vector, and then the numerator is always going to be 0. So we'll take the 0 vector to be orthogonal to all vectors. I know that that's a little bit awkward from what's in the parentheses, but it's just simply a convenience. And likewise, we also take the 0 vector to be parallel to all vectors. And I want to change colors for this. We take the 0 vector to be parallel to, oops, I didn't want to do that. 0 vector to be parallel to all vectors, and I'll give you a reason for that. Here, I'm ready to change colors. So suppose I have a line through the origin, say y equals x, and I draw some of the vectors in y equals x. There we go. Draw some of the vectors in y equals x. I'm getting a line, and every vector whose endpoint is on that line is parallel to every other vector whose endpoint on that line, except for the 0 vector. That would be very awkward. It would be awkward to have one single exception to that perfectly general rule. So instead, we're just simply going to take the 0 vector to be parallel to all vectors. So it's a convenience. Okay? So the difficulty with the dot product is not doing the computations, very straightforward computations, and it's not understanding orthogonal or parallel. So what is the difficulty with dot product? And the answer is it's difficult to know exactly what it is. I mean, if you take, for example, real numbers and do some kind of combination of real numbers like addition, we understand that 3 apples plus 5 apples makes 8 apples. If you do multiplication, we understand that you have a rectangle with 3 on one side and 5 on the other, and so the total number of square inches is. But what's the deal with this particular combination of vectors? What does it mean? So the corollary suggests that one way to understand what dot product means, that between your ears you say to yourself, aha, what that means is, one way to understand what dot product means is that it's a measure of how orthogonal vectors are. That vectors where the dot product is close to 0 are nearly at right angles. And so I have a picture to illustrate, of course I do. So I am going to, here, I'm going to click to watch that vector, to have that vector become more and more right angles to the vector I. And over here I'm showing the angle. So I took pi over 2, that is to say 90 degrees, pi over 2 minus 0.4, and then I'm going to take pi over 2 minus 0.3, and pi over 2 minus 0.2, like that. And so as the vector becomes more and more like a right angle, as theta becomes more and more like a right angle, I'm going to watch the dot product on the other side of the table. So here we go. So pi over 2 minus 0.4, pi over 2 minus 0.3, that's pi over 2 minus 0.2, pi over 2 minus 0.1, it's becoming very much like a right angle, and finally pi over 2, you get 0 for a dot product. So in some sense, what dot product measures is how near the vectors are to being orthogonal. As theta grows from 0 to pi over 2, the dot product will shrink from 1 to 0. Okay? So in some ways, you can understand what dot product means as it just drops out of the algebra. Okay, great. And in some ways, you can understand what dot product means is by this picture, is that as the vectors come to be more and more at right angles, they come to have a dot product that is closer and closer to 0. I did the positive dot product case. You could do the negative dot product case. Anyway, the point is, orthogonality is the same thing as 0 dot product. Okay, so practice, please. So we're applying the angle formula that we just had on a couple slides ago. Here we go. So the arc cosine of minus 13 over the square root of 290, and my calculator said such and such many radians. Likewise for the three tall vectors, I got so and so many radians. Find the angle between these two vectors. Okay, great, and my calculator gave me 1.288 radians, and once again, I want to emphasize a point here, is that the way in which question number 2 is different than question number 1 is that these are four-dimensional vectors. If you asked me to draw a picture in question number 1, I'd have no trouble drawing a picture here and taking out a protractor. I'd have some trouble here, but I'd figure it out if you look at it from the correct direction. But down here, I just simply could not draw a picture of 4 dimensions. I just can't. I mean, maybe somebody else can, but I can't. But nonetheless, I can do perfectly good geometric type of things in 4 dimensions because I'm doing them algebraically. Next. Okay, so it asks, are the vectors orthogonal or parallel? Now the first vector looks like it might be a 2 tall vector, but it just simply is 2i plus 0j plus 1k, and the second vector is manifestly a 3 tall vector. So is it orthogonal? Is it parallel? And you just do the operation. Dot product is 6 because the dot product is not equal to 0. The two of them are not orthogonal. Because the dot product is not equal to the product of their lengths, the two of them are not parallel. Okay, so just continuing on doing a little bit more based on having thought about dot product. This is another one of those 3D things, so I'm going to go to the 3D picture here. Let's see, I got to click forward before I get to it. So I'm, boy, excuse me, there we go. So I'm ready to go to the 3D picture. There we go. Okay. So again, sometimes folks in this section have a little trouble picturing what's happening because this is, for some folks, the first time they've thought about 3D space. So it's just a bit of a puzzle. Here it is, 3D space. The part that seems to give people trouble, in my experience, is not the angle between the vector and the x-axis, called alpha here, or the angle between the vector and the y-axis, called beta. It is instead somehow the angle called gamma. That is between the vector and the z-axis. For some reason, that gives folks a lot of trouble in the picture. Maybe it's my inability to draw it, but anyway, it does give folks trouble. So sometimes if you have a 3D and you wave it around, a person can see it better. The direction cosines are the cosine of alpha, the cosine of beta, and the cosine of gamma. So the cosine of alpha, for example, we would take V0, V1, and V2. Dot product, trying to make the dot especially bold, 1, 0, 0, because that's the vector that defines the x-axis. And then over, length V multiplied by length I. Length I is 1, so I've dropped it. And in the numerator, V0 times 1, V1 times 2, V2 times 0, so I only kept the V0. There we go. Okay, and then the same thing for beta and the same thing for gamma. Okay, and I have an example here. So V is 2i 3j minus k. It's just numbers. You punch it out, you get, for cosine of alpha, you get 2 over radical 14. For cosine of beta, you get 3 over radical 14. For cosine of gamma, you get minus 1 over radical 14. You could go on and take the arc cosine to figure out the angles, but it often turns out that we only want the cosines of those angles, so you could stick with the cosines. Okay, so practice, please. Okay, and it's just what you think it is, 2 over radical 21 minus 1 over radical 21 and minus 4 over radical 21. You're just simply applying the formula. Next one. So V lies on the x-axis. What's cosine of alpha? So if V lies on the x-axis, then there's two possibilities. V can lie, oops, made a stray mark, sorry. If V can lie on the positive x-axis, or V could lie on the negative x-axis. So changing colors here, if V lies on the positive x-axis, okay, then the angle is 0, and the cosine of an angle of 0 is positive 1. If v lies on the negative x-axis, then the angle is pi, and the cosine of pi is minus 1. Okay. Okay, so we've done dot product, and we're going to use it to do the orthogonal projection. We've done dot product, and we have some intuition about what it means, and the fact that it is, in some sense, tells us about the geometry. Okay, so here I have a picture, goofy picture that I got off the internet. This person is trying to drag, I think it looks like a heavy rock to me. And of course, when you try to drag the heavy rock, you're slowed down by friction. Friction acts in that direction. They're parallel to the ground. Okay, I mean, if you lifted the rock straight up, you wouldn't feel any friction at all. Presumably, the rock is too heavy to be lifted straight up. So this person is not opposing the arrow directly. This person is only opposing the arrow somewhat. Okay, so this person is not pulling in the direction opposite to the arrow of friction. Only some of this person's effort is opposite to the arrow of friction. So given two vectors, we can ask how much of v lies with s. That is, how much of v lies in the direction of s, or in this case, in the opposite direction. Okay, so here we go. We're asking, given a v and an s, see v and s, we can ask how much of v lies in s, and it's not all of v in this picture. Okay, so the thing to think is that I've got a person down here walking up the s vector, walking up, and looking over their head, but that is to say looking at a right angle over their head. Not straight up, that's not right. Instead, looking at what makes a right angle with what they're walking on over their head. I've got that in as a dotted line. So putting things in terms of letters here, I want to find at what point that tip of v is directly over that person's head. And so for what c is c times s, give you this picture. So said another way, for what real number c is v minus cs perpendicular to s. So I want v minus cs to be perpendicular to s. And we know that that calls for dot product equals 0. There we go, dot product equals 0. That's why it's here. So dot product equals 0. I multiply through by the dot product. That's one of the rules of dot product. Multiply through by the dot product, and I solved for CS. There we go, solve for CS, and I got S dot V on the top of the fraction, S dot S on the bottom of the fraction, times S. Okay. So if you take S to be a non-zero vector, the orthogonal projection of V onto the line defined by S is this. V dot S on the top, S dot S on the bottom, times, that's not a dot, right? Right? You've spotted that that's a real number, that's a rescaling operation. So this fraction is scalar over scalar, so that fraction is a real number, and then real number multiplied by the vector S. People often call this the orthogonal projection onto S, but I got to tell you that's somewhat misleading. The part where it says onto the line defined by S matters, is that if you had, for example, if you had a vector S like so, and a vector V like this, and I said, what's the projection of V onto S? Well, the projection of V onto S really is a projection of V onto the line given by S. So we're looking at something that extends past S. So S defines the line, but S isn't the entirety. Okay, anyway, so you do often run across people say the orthogonal projection onto S as a shorthand for the more correct term up top. Anyway, it's a formula that we're going to memorize. So we sometimes want the length of that projection. We'll rewrite the denominators S dot S as the length of S squared, and we'll use one of the two parts of the square to normalize S's length. There we go. Now we have a length 1 vector, and so the length of the projection is the scalar multiple's absolute value. There we go, the scalar multiple's absolute value. Okay. But we're especially interested in that projection formula on the top of the slide. So please, for some practice. Okay, simply applying the formula v dot s over s dot s multiplied by s. And you just get some numbers and you multiply through. They all happen to be divided by 19s. Anyway, you get what you get. Second one, decompose A into the sum of two vectors, one parallel to B and the other perpendicular to B. So that relates to this picture here. We've got a vector A and we've got a vector B. And we want to decompose A into the sum of these two vectors. This one right here, the projection, and this one right here, the perpendicular to the projection. Okay, please. Okay, great. So the earlier picture says we want the projection of A onto B, and we want A minus the projection of A onto B. And so I calculated the projection of A onto B, there it is, and then I took it away from A, there it is. Okay, so for the two vectors from the prior slide there, find the length of the projection of A onto B. And it's just a question of applying the formula. You take the absolute value. So this is, again, there's a little bit of typing here. This is the absolute value. And this is the length. The absolute value of A dot B, divide by the length of B, and the calculation just gives you 5 over radical 11. Okay, you could also have done the calculation by finding the length of the projection vector. That's fine. You got the same answer that way. That's fine too. True or false? The value of the projection of S onto V in this picture, the value of the projection of V onto S, say it again because I said it wrong the first time. The projection of V onto S is 0 because V points in a direction that's generally opposite to S's direction. Okay, and this is one of those questions that I wouldn't have asked if it was true, so it must be false. So what we're saying here is that actually you are projecting onto the line defined by S. And when you project onto the line defined by S, you do get a vector, perfectly good vector. I know that the vector that I've got there is not on top of S in any way, but it's nonetheless the perfectly correct answer, and it's not the 0 vector. Okay, let's try. So false. The projection of V onto S is really the projection onto the line through the origin that contains S. Let's say the line defined by S. Okay, next one. What's the projection of V onto V? And the answer is if V is unequal to 0, then it's V. But if V is equal to 0, then it's undefined. Projection is defined for non-zero vectors. Okay. Here, find the projection onto S of V. And a person just follows the formula, you just get what you get here. But the point again with this question is that we are able to do geometry things, such as dropping a perpendicular, in a space where I cannot draw a picture. So we are able to do in 4 dimensions, 5 dimensions, 6 dimensions, but I didn't want to have 400 tall vectors. So we're able to do in dimensions where we can't draw a picture, we're able to do geometric things. Okay, so that's those are the points about dot product that I want to get to. I have 2 extra things to say here, 2 sort of bonuses. A lot of this material is got sort of interesting sidelights, and the first is that we saw the formula earlier in the course. We saw the formula for cosine of beta minus alpha, and I've just simply said, look, you saw it in high school trigonometry. And so I just quoted it from somewhere. I brought it in from the outside. But the work that we just have done, it provides a way to give the cosine of beta minus alpha quickly. So I want to do it as an example. So you see here 2 vectors. U is cosine alpha sine alpha. V is, I said that backwards. U is cosine beta sine beta. V is cosine alpha sine alpha. And here's the angle between them. I can call the angle theta. There we go, theta. So here's theta. The angle formed between U and the x-axis, I'm calling beta, and the angle formed between V and the x-axis, I'm calling alpha. So this is the same thing as cosine of beta minus alpha. Anyway, I know how to find the cosine of theta. There it is. It is the dot product of the 2 vectors over the length of the 2 vectors. And there it is. I took the dot product of the two vectors, and the length is 1 and 1, so that basically disappears, and I'm just looking at cosine beta, cosine alpha, sine beta, sine alpha. Okay, so the formula that we saw when we were doing trigonometric integrals early on in the course, in fact, drops out of what we're doing now. I quoted it then as having something to do with trigonometry class, but here it's easy to see. Next, I talked about the triangle inequality in the previous deck of slides, but I want to use what we have now, dot product, to go through it. The triangle inequality has two separate sentences. The first sentence is the familiar one. Any two vectors satisfy that the length of u plus v is less than or equal to the length of u plus the length of v. That is to say, if you're going to go straight from one place to another place in space, it is longer to go around. So if you go straight from the origin to u plus v's endpoint, that is shorter than or equal to going first along u's vector and then along the v vector. Okay, so the shortest distance between 2 points is in a straight line, familiar. The second sentence is maybe less familiar, is when do you have equality? Less than or equal to, when do you have equality? And the answer is you have equality if and only if one of the vectors is a non-zero scalar multiple of the other. So here, for example, are two vectors where one of them is twice the other. If you laid those two vectors out end to end, you would have a straight line, and so the triangle inequality would give you equality. All right, so I want to briefly go through the formulas. The work that we've done gives you the triangle inequality reasonably quickly. So here we go. I'm only actually going to do the first sentence, and I'm going to just wave at the second sentence. So here I'm interested in this. I want to show that that's true. So all three numbers are positive. The lengths are always positive or zero. So the inequality holds if and only if the square holds. So I squared the left-hand side and squared the right-hand side. That says length of u plus length of v, quantity squared. So the triangle inequality holds if and only if the first line holds, which holds if and only if the second line holds, which holds if and only if the third line holds. We haven't got to those lines yet, but we're working on it. Okay, let's see. So the length of a vector squared is the vector dotted with itself. That's the left-hand side. And what happens when you square two numbers? We know what happens. You get the first number squared, then the middle term, and then the second number squared. Okay, so I'm just simply following it through here. When you take u plus v dotted with u plus v, I'm distributing the dot here, u dot v, and then the v dot v. So I just expanded the left-hand side, and here I'm recognizing the length of u quantity squared as u dot u and the length of v quantity squared as v dot v. So I'm simply doing the algebra. That's all. Just grind, and again, triangle inequality holds if and only if this line holds, which holds if and only if this line holds, which holds if and only if this line holds. And what happens on the next line? And the answer is I see that there's a u dot u, cancel with the u dot u. I see that there's a v dot v, cancels with the v dot v. And then here I see a u dot v and there it is, v dot u. Of course, u dot v and v dot u are equal to each other, so I just wrote that as 2 times u dot v, and I just copied that down. That's the right-hand side copied down with the cancellations done. Okay, so I'm working on if and only if and only if and only if, and I boil it down to actually kind of a remarkably simple statement here. If you cancel the 2's, u dot v is less than or equal to length u times length v. Anyway, so I'm going to at this point do something that is a little bit tricky. I apologize, but I'm up to something, and so it's not brutally tricky, but just not the first thing you would think to do. I'm going to multiply both sides by both length u and length v, but I'm going to, on the left-hand side, I'm going to do it in a somewhat peculiar way. So let me do the right-hand side first. I'm multiplying the right-hand side by length u and length v, and those are both positive numbers, so they'll leave the inequality unchanged. Multiply by length u made it a length u squared. Multiply by length v made it a length v squared. Now we go to the left-hand side. I took u dot v and I multiplied by length u and length v, but I did it in a somewhat surprising way. I have, instead of writing length u times u, I wrote length v times u. And instead of writing length v times v, I wrote length u times v. And I'm up to something. I won't be up to it for 20 minutes. It'll be over in just a second. But I acknowledge this is not the first thing a person would think to do. Why am I doing it? And the answer is that if I move everything to one side of the equation, there's the length u, length v, length u squared, length u, v squared, and there's another length u squared, length v squared. That makes two of them. And when I took this stuff here and moved it over to the other side of the equation, there it is. Other side of the inequality, there it is. So I have, so far, I've done something a little tricky, I acknowledge. I've done something a little tricky, but I have triangle inequality holds if and only 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 if. I'm about to change to the next slide because it just simply didn't fit all in one slide. But that expression right there, that expression factors. That's why I was doing this somewhat tricky thing, is that expression factors into length u times v minus length v times u dotted with itself. And so I have triangle inequality holds if and only if a vector, this certain vector, but anyway, this vector dotted with itself is greater than or equal to 0. And of course, any vector dotted with itself is greater than or equal to 0, so it's true. So this statement is true, and so all the statements on the prior slide are true, and so we have that the triangle inequality is true. Okay. Again, the triangle inequality has two sentences in it. One sentence we've done, and the other sentence here. Here's the proof for the other sentence. I'm not going to do it. It's just simply more obscure. But nonetheless, you recognize that the parts are the kind of things that we've been doing without reading it closely. You should read it closely. I urge you to. But without reading it closely, you can recognize that the parts are the kind of thing that we've been doing. Okay, very good. Okay, so I'll let you go, and when we come back, we're going to see a different vector operation, and just different than dot product, and so we're making our way through some elements of vector operations. Very good.